And now I'm going to try to hand the presentation off to Mr. Ryan Sarda, who I briefly introduced earlier, but Ryan has certainly become a leader in our industry and has currently taken on a new chapter in his career, joining Dandelion. And I'm anxious to hear a little bit more from Ryan, but I'll let you guys read the screen, and I'm going to try to hand off presentation role, past presenter role. Did you get a little pop-up there, Ryan?
Can you hear me, John?
I can.
Yeah, so I don't have a pop-up. I'm sorry, this has been really difficult.
I'm wondering if I could log into the software, at least, and then I can give you mouse control.
Oh, that would be great. For some reason,
see if I can do that.
Yeah, let's try it. So I apologize, everyone. Thanks for having me, John.
Okay, where do I go for your software?
Okay, looplinkrlc.com.
Okay, let me cancel the presenter. And share mouse control. Oh, look at that. You're in charge.
Is it working?
Yeah.
Okay. Man, I've been panicking for the past hour, trying to figure out how to get this to work, but you know, where there's a will, there's a way.
That's right. We will not be denied.
Yeah.
Can everybody see my screen still?
Okay. Well, as long as you guys can still hear me. So, yeah, as John meant, sorry, can you hear me, John?
Yep.
Oh, there you go. Okay. So, as John recently mentioned, I recently joined the team at Dandelion on the engineering team there. Before that, I spent the last about 15 years or so building geoconnections from the ground up. Most of what we focused on at the company was trying to find ways to make geothermal more approachable. As John mentioned, we did a lot of education and outreach, ICSPA training, etc. And since then, we moved to developing software, just like LoopLink RLC. Now, part of what we're doing at Dandelion is integrating some of these tools into a platform there that we're hoping will really move the industry forward in terms of, as you guys know, in spending time with John through these trainings and all the other presenters that have been involved, there's a lot of knowledge in the industry that's been gained just through experience and everything else. Our goal at Dandelion is to try to distill some of that information and kind of disseminate it, I guess you would say, through the use of tools, just like LoopLink. John's been kind enough to invite me today to give you a quick demo of the program here. For those who don't know how to get to it or haven't heard of it, you can simply just go to looplinkrlc.com to create an account. And actually, LoopLink now, since we've joined forces with Dandelion and made that move, LoopLink is actually free for everybody to use. So back in the old days, we used to bug you for login information and credit card, and we had to get paid once in a while. But now it's completely free. So you guys, you see this program, and like what you see, you can just go ahead and hop on and play around with it yourself. So for the purposes of today, let's go ahead and create a new account, or create a new project, excuse me. I'll just kind of give you an idea of how this program works. Notice that after I click the Create New Project icon, it's going to force me through a couple of pages initially just to set up the project. We push you around for the first few pages, and then once you get those created, then we're done pushing and you can kind of work through the program however you prefer, however you see fit. But you'll notice when you get to the page there are some required fields highlighted by red text here and here. So once you fill those out, you can go ahead and save the page to move on in the program. And just to give you a quick tip before we get too far, the Save button is always fixed on the upper right-hand side of the page here. You can click on that, or as long as you've got a cursor blinking inside of any field on screen, you can just go ahead and hit the Enter key on your keyboard, which I'll do right now. Notice that once I hit Enter, I got a successful save message across the top, and then it'll let me move on to the next part of the program. Notice how, as we progress through these pages, how the project builds itself out over here on the right-hand side. So first thing you have to do is name the project. I'll just leave it at the default client name. We have to go ahead and choose or specify a weather data location. And I'm sorry, John, what's the nearest? I don't know. What's the nearest bin data location for you, John?
How about Syracuse?
Syracuse. Oh, yeah, done. There you go. Okay. So once you've selected your bin data method, notice that the design conditions, average outdoor air temperature, pop up for the location. Next step of the process is to define what kind of building you're working with. This selection here on screen actually defines the balance point temperatures that you can see. For a house, the default balance point temperatures are 57 heating, 65 cooling, and basically what that's saying is as long as the outdoor air temperature is 57 degrees or warmer, you don't need to add heating to the building, or if it's 65 degrees or cooler, you don't need to air condition the building. And then between 57 and 65, no heating, cooling required. It's basically a dead band where you don't need any space conditioning. We'll go ahead and leave it at the default setting for a residential application. And then the very last thing that you need to do is specify your ground loop design parameters. Generally speaking, 30 degrees minimum, 90 degrees maximum are default values for most programs. Specify your deep earth temperature. Generally speaking, if you aren't sure what it is, you can usually estimate it to be a few degrees above the average air temperature for the bin data location that you've specified. You'll notice that we've actually got a little button here that'll calculate it for you based on the bin data that you've loaded up in the program. So I'll go ahead and click that button. It'll think for a minute and notice now that it estimated the deep earth temperature to be about 52 degrees. As far as the minimum and maximum EWT values are concerned, 30 degrees is a good starting point for a heating dominant application. 90 degrees, I'm going to go ahead and default that to about 30 degrees above the deep earth temperature, so at 80, to get us a little bit closer to what we might be able to reasonably expect our ground loop to provide in cooling mode, considering that we're not probably going to work our ground loop as hard in the summertime as we do in the winter, being a winter heating dominant climate. So I'll go ahead and hit Enter here. And now that the project details page has been saved, you'll notice we are next taken to the prices and inflation rates page, where you can go ahead and specify electric rates. Notice that there are some required fields on this page as well. John, do you have a good idea of electric rates in your area? I'm sure you do.
Yeah, let's use about 14 cents.
14 cents for everything?
Yeah.
Okay. Notice that you can break out your electric rates. If you get an incentive for, let's say, geothermal heat pump versus standard, some might give you a reduced rate on electricity. And I'll just pop in some sample prices here for propane and fuel oil as well, just so we can, when we get to econ, we can take a look at what that would look like. Then once you pop in,
natural gas, I think, is less than zero. It's so damn cheap.
Yeah, I don't even want to talk about that dirty word, so thanks for bringing it up. Okay, and then the next thing, that you can specify on the page are any fixed costs that you have. So, for example, if you've got a propane tank, the homeowner's got a propane tank in their backyard, but they don't own it, they pay to rent it or lease it, whatever, and somebody maintains it, qualifies it every year, whatever. You can actually put in that lease cost here and account for it through the econ analysis later on in the program. So some of those things, let's say you've got a natural gas meter that maybe costs you $10 a month, whatever it is, you can pop those costs in as well. I'm going to ignore natural gas because it's a dirty word and we don't want to talk about it anymore. And then the last thing that you want to specify are your long-term inflation rates. And notice you can specify separately electricity versus fossil fuel-based systems. I'll just go ahead and leave it at the defaults. And notice these aren't program defaults. These are defaults that I've actually stored under my account. So you'll notice I've got a slightly different electric inflation rate compared to the rest. But go ahead and save that page now. And you'll notice now that these first 3 pages have been filled out: client information, project details, and prices and inflation rates. Now we're pretty much done pushing you around in the program, and you can move however you see fit, however you prefer inside the program. Obviously, once you get these first 3 pages set up, the thing that makes the most sense is to add some sort of a load element to your project, either a dedicated hot water generation zone, or in this case, I'm going to go ahead and add a space conditioning zone by clicking on the Add Zone button. As soon as I do, you'll be taken to the zone page where you can go ahead and name your zone. I'm just going to call it block load for the entire house here. For the sake of example, let's pop in heating and cooling load. These are going to come from the results of your ACCA Manual J load calculations that you performed. Let's just say maybe 45,000 BTUs per hour in heating mode, and maybe, I don't know, 28,000 BTUs per hour in cooling mode. You'll typically see a similar ratio in terms of heating to cooling load in the area in New York. Once you've specified that, you can change your heating cooling set points as necessary, your space sensible heat ratio. I'll leave that at the default 0.9 since we're just using sample loads anyway. The next thing on the page that you fill out is the heating offset value. Now if you think about what we're doing when we're talking about heating and cooling loads, we're talking about worst case. So on the cooling side, worst case is when you've got some people in the building, normal occupancy, not when you've got a big 4th of July party or something like that, but normal occupancy. You've got lighting, got some cube heaters, you've got a few appliances running, etc. That's generally considered to be worst case, is when you've got all those things going on inside the house and it's on the hottest day of the year. On the heating side, worst case is generally on the coldest day of the year. But when you don't have any internal gains, you don't have any solar gains on the house, you're not accounting for internal heat generation due to people, lights, appliances, etc. This is an absolute worst case number. But generally speaking, that peak heating load doesn't necessarily reflect actual usage of the building, right? From normal everyday usage, people living in the space, etc. And that's exactly where this heating offset value comes in. What you want to do is try to account for normally occurring internal heat generation, right? So if you know a value for that, you can put it in directly. No, I lost my train of thought there. But if you don't know a value, we've got a little calculator here. If you click on Estimate Heating Offset, as soon as you do, it'll bring up a little worksheet that you can fill out. And let's just say, for the sake of example, this is a 1,500 square foot house, maybe 4 people living there. Slightly active. Oops, the mouse is a little tricky. And then maybe they're there 7 or 8 hours a day, whatever it happens to be. Notice once I get a subsection filled out, it'll show the subtotal in each section and then the grand total on the lower left-hand side of the screen. We can go ahead and say maybe we've got average lighting in the house, and that's maybe used 5 or 6 hours a day, whatever it happens to be. I'll go ahead and pop in 6. And then maybe in appliances, let's say we've got 1 water heater, 1 refrigerator, and 1 freezer. So once I get all those values entered in, notice my heating offset on the lower left-hand side. I'm just going to go ahead and hit apply and bring that value into the field here. So this is the naturally occurring internal heat generation inside the home that you can account for on the heating side. It offsets the amount of heat that you would normally have to add with the heat pump, reduces predicted runtime a little bit, and predicted operating costs, etc. So beyond that, next stage of the process is to go ahead and specify heating and cooling start temperatures. Heating start temperature is actually calculated based on the ratio of heating offset value to your peak heating load. So you don't have direct input over that, but the cooling start temperature you actually do. If you think about how a homeowner uses a building normally, even though theoretically we would need to flip on the air conditioning when the outdoor temperature is 65 degrees or above, most homeowners probably aren't going to do that. They'll probably just go ahead and open the windows until it's maybe 75 degree outside air temperature and above. And for that dead band between 65 and 75, they're just running no air conditioning with the windows open. So with all the load information and start temperatures specified, the next thing you can go ahead and do is choose a heat pump. So for this example, let's just go ahead and take a look at a forced air unit, maybe look at the dual capacity. And we can go ahead and grab, since John was talking about water furnace, I believe, let's go ahead and grab a water furnace.
No, I want, do you have GeoStar there, Ryan?
Oh, you do. I'm sorry.
Yeah.
There we go. Let's go with the GeoStar units. I should have known better. Okay, so with the GeoStar units, you notice all of the dual capacity units that are models that are available. We can go ahead and grab a unit. Let's go ahead and, for the sake of example, take a look at a 5-ton unit just to start out and see where we end up. Keep in mind that with a 30-degree minimum EWT value, you only get about 80% of the rated capacity off of the unit. So this being a 5-ton unit with a 30-degree loop, you're probably going to get between 45 and 50,000 BTUs per hour of actual heating capacity under design conditions. And notice that as I scroll down here on the page, that 5-ton unit gives me the 47,600. So about 4 tons of actual heating capacity in heating mode with a 30-degree loop. But take a look in terms of our percent sizing relative to the peak heating load. We're 105% sized. We're getting basically 100% of the energy from the Geo unit, not relying on supplemental resistance heat at all. But looking at the cooling side here, I assume you guys have probably talked about cooling sizing strategies. Generally speaking, you'd like to see this percent oversizing in sensible cooling capacity relative to sensible load. 25% is kind of the target. Obviously, it's not a make or break deal, but that's optimal what you're trying to shoot for here in terms of percent oversizing. The reason that we choose a dual capacity unit is because then you can check part load capacity, percent oversizing on cooling in an area where our cooling load is much smaller than our heating, and then check the heating sizing in high speed, which is what you're designing for in this case. I'm going to back up and choose a different unit because we could probably take a look at another one that might fit the system a little better with respect to first costs relative to operating costs. But just taking a look at this 5-ton unit now, you can see the predicted low capacity runtime in heating mode is about 2,200 hours versus 200 hours of high speed runtime. So not a whole lot of hours relatively speaking in high speed for this unit. And then obviously on the cooling side, we're running in low speed 100% of the hours of the year. Based on the heat pump we've selected, you can see predicted heat pump energy use. We know the efficiency. And then based on the 14-cent kilowatt electric rate, you can see the predicted heating and cooling costs right here. So our total operating costs are about $1,200 for the year to heat and cool this house as we've entered it today. But keep in mind that it's with a 5-ton unit. Looking here, that covers 106% of our peak heating load and 100% of our heating energy requirements right here. But just say, for the sake of example, let's go up here and maybe flip to the next smallest unit just to see what that would look like. Obviously, when we go to a smaller unit, it's going to be slightly undersized relative to the heating load. I'm going to go ahead and grab an ND049, which is that 4-ton dual capacity unit. Let's scroll down and take a look at what that looks like. So now we're at our 4-ton unit. And you can see relative to the peak heating load, we're only about 80% sized. And generally speaking, what I try to do when I'm designing a system is shoot for about 75 to 80% sizing. Because if you take a look here, 80% sized relative to the peak heating load, but we're still getting nearly 99% of the energy from the Geo unit, and the balance is being made up by our supplemental electric resistance. So we're not paying a whole lot of penalty right now for backup heat just by being undersized. But now take a look at our part load Cooling capacity here, 30% oversized relative to the peak cooling load. A slightly better fit for this system. Still covering most of the energy requirements in heating and much closer to that 25% guideline that we try to shoot for in cooling side. So for the sake of this example, I'm probably going to stick with a 4-ton unit for this space. And you can see, obviously, the heat pump runs a few more hours in high speed. We get a few more supplemental bin hours, but look what happened to the operating cost. It wasn't drastically affected at all. Supplemental costs went up a little bit, but we're still at about $1,200 total operating costs in heating and cooling combined. But if you take a look at the bin load profile graph, you can kind of see what's going on here. The green bars here are the bins, the number of hours in each temperature range. And you can see outdoor air temperature on the bottom x-axis here, and you can see bin hours on the left-hand y-axis here, building load or heat pump capacity here on the right-hand y-axis here. So what just happened is we had a heat pump that was covering 100% of the load, so it was sized all the way out here. When we went from that 5-ton to the 4-ton unit, you can see we slid our balance point all the way back to about between a 5 and 10 degree balance point temperature right here. So what we mean by balance point temperature, as soon as the outdoor air temperature falls below this point in this tan shaded area, that means the heat pump and the supplemental resistance heat are going to have to run at the same time. But you can see by sliding the balance point temperature all the way back here, we're still not catching a whole lot of bin hours for possible operation in that zone. So even though we're only 80% size relative to the peak heating load, in this last 20% of the load that we tried to pick up with that 5-ton unit, there's not a lot of hours, so we're not really affecting our bottom line in terms of operating costs. So I hope that makes sense. So you can see all these hours here. The low line here is part load heating capacity. So all the hours to the right of this intersection, that's all part load heat pump operation. Everything between this line and this line is full load heat pump operation without supplemental, and everything to the left here beyond that, all of these hours are heat pump plus supplemental operation at the same time. So that kind of gives you an idea of what the weather looks like and what that all means in terms of heat pump sizing relative to runtime, relative to operating costs, which is really what we all are most concerned with. So with that, let's go ahead and save this zone. Now notice as soon as I do, on the right-hand side, you see how the project has built itself out now. We've got our 4-ton block load zone inside of the navigation here, but nothing else that we've really added to the project just yet. Zone summary page is going to show a breakdown of all the zones that you've added to the project. In this case, it's not really interesting just yet because we've only got the one zone. So let's go ahead and make this example just a little bit more interesting. Let's say the homeowner has a forced air unit for the house, but maybe they want to get fancy and they're going to add a garage, right? And let's just say they've got 20,000 BTUs per hour of just heating load. They want to heat the floor with a radiant system. So I'm going to go ahead and put a 20,000 BTU per hour heat loss on that side. I'm going to go ahead and choose a water-to-water unit. I'm going to have to provide some guidance here. We've got, there we go. The smallest unit we've got is a 3.5-ton unit. We'll go ahead and grab that. So now, skipping over all these other details, because you guys get an idea of how to interpret the page and what's going on, I just wanted to go ahead and save a second heat pump onto this project, make it a little more interesting when it comes time to design the ground mount. So let's go ahead and save that. Now notice I've got two zones. I've got a block load for that forced air system in the house, and then I've got the garage zone, which is the radiant water-to-water system that we've just added, heat-only zone. Now if you go to the zone summary, you can see we've got our 4-ton unit forced air, 3.5-ton unit water-to-water. You can see combined heating loads. You can see combined installed COPs and average COPs, combined flow rates. The other thing that you can see are your combined operating costs on the bottom of the page. And you can see your combined heating ground load versus your cooling ground load. So this is the amount of energy that we take out of the ground loop in the winter heating season. this is how much we return back to the ground loop in the summer cooling season. We've got a fair amount of ground load imbalance here because we heat so much more than we cool, and that's a number that you'll see reflected in the ground loop design here when we get to it in a second. So, are there any questions on that so far?
Now, is this do you always use this software?
Do I always use the software? Yeah, I do. Oops, no, that didn't work. Is that a loaded question?
No, I was just wondering.
Okay. Yeah, I do. You know, I rather like it since it's the one that we built. So, okay, so now we've got our two zones added to the project. I'm going to go ahead and add a ground heat exchanger to the project. And for the first pass, let's go ahead and take a look at a vertical bore system. Okay, so now I had plans to show you a site where we could actually look up the average formation thermal conductivity value, but the address is very difficult to remember, so I'm going to pass on that for right now. I'll be in New York tomorrow or for the rest of the week, so you guys can hit me up for that website. But basically what it is, you can search for mineral resources with the USGS, and basically they've got a site where you can actually look at the map for every single state in the U.S., and you can actually search by latitude and longitude, punch in coordinates directly, and it'll actually give you the USGS value for the soil type on that specific area. It's pretty cool. So while I was messing around preparing for this review, I actually did it for John for your address, 3523 County House Road, right? And it showed was it limestone?
Oh, yes.
Shale.
No,
Pretty
limestone.
Pretty much limestone, right?
Yep.
So going to a site like that, you look up limestone. Let's just go ahead and pop in, I don't know. It asks for the depths so that you can calculate a weighted average, basically, of connectivity. But I'm just going to say, since it's all limestone, let's just go ahead and grab limestone. And then you can see on this little connectivity calculator how you can build out a weighted average if you'd like. If you've got various layers of, let's say, shale versus granite versus limestone, whatever they happen to be, you can actually build that out here on this calculator, adjusting your moisture level or density values, low, average, high. We tried to keep this fairly simple, but generally speaking, I recommend leaving those values at average unless you've got better information and you know that the water table is fairly low or it's fairly high in an area, whatever it is. You can adjust that up or down as needed. I'm just going to leave that at the default value and hit apply. And as soon as I did, notice limestone is pretty conductive in terms of heat transfer. But I'll go ahead and use that 1.8 formation thermal conductivity value. Once you've got your soil properties popped in, next thing you need to specify is your loop type. We've got our two basic kinds of HDPE, which actually don't affect the calculations at all. And then there's thermally enhanced HDPE and PEX-A if you want to try to use that in the ground loop as well. I'll just leave it at the default HDPE material. And then the next thing that you need to specify is your U-bend diameter. U-bend diameter, basically when you design a ground loop, what you try to do, you're balancing all these different concepts at the same time as you make these decisions. You want to be able to balance flow in your loop field. You want to be able to achieve turbulence without excessive head lice, so that we maximize heat transfer in the ground loop without paying for a whole lot of pumping penalty. And I'm sure you guys probably saw this image here. I just clicked on the help icon, but you probably saw this image in the RLC manual and throughout the IGSPA PowerPoints. But basically, if you follow the rules of thumb that are kind of shown on this drawing here, you will have a layout that's guaranteed to have turbulent flow in the loop field without excessive head loss. Basically, with a 3/4 inch ground loop, you want to design your field for 1 loop per ton. Okay, so you can see this is a 3-ton example shown in the drawing here. So 3 loops, 3-ton loop field, 1 loop per ton. Translating that to a larger pipe size, generally with 1-inch pipes, you want each loop to represent 1.5 tons. So notice that the depth for these 1-inch counterparts are 1.5 times deeper than the 1 ton option in the 3/4 inch, and the flow rate is 4.5 GPM, which represents 1.5 tons of capacity. And now generally going to your 1.25 inch option right here, you want your 1.25 inch loops to represent about 2 to 3 tons of heat pump capacity. Notice that as your pipe sizes get larger, they get to be quite a bit more forgiving in that it takes less flow. There's a much larger gap between the minimum amount you need for turbulence and the maximum amount that you can accommodate before your head loss becomes a concern. So generally speaking, 1.25 inch loops are probably 2 to 3 tons of pop is what you're trying to accommodate in terms of flow rate with those. So knowing that, we've got a 4-ton unit in the space. We've got a 3.5 ton unit in the garage, so 7 tons or so. What I'm going to do, for the sake of example here, is go to an 1.25 inch loop. You have to enter in a bore diameter. Generally, it's going to be between 4 and 6 inches. Doesn't greatly impact the calculations that much. I'll just pop in 6. And based on the rules that I just gave you, I'm going to try to get away with 2 bores here. 2 bores, spaced 15 feet on center with a 0.4 grout connectivity value. Just show you a couple things to be aware of here. Now that we've done that, first thing that you always want to look at is how many GPM you're pushing through each loop, or the GPM per flow path. You can see 11 GPM through an 1.25 inch loop. Especially down here, you can see they're coming out to almost 600 feet. You'll definitely want to check your numbers here and make sure that at that flow rate, your head loss isn't becoming excessive and pumping power is going to become a concern. So 11 GPM might be on the high side. Might consider going to 3 loops instead of the 2 for this example here in the 7 tons. So we're going to get closer to about 2.5 GPM or tons per loop. So now notice I just bumped my bores per row to 3. So I've got a 1x3 bore field layout. So 3 bores total, 7.3 GPM per loop. And keep in mind that's when both of these heat pumps are running in the heating mode, which is what we're going to be most concerned about. So 7.3 is right in that sweet spot of 2 to 3 tons per loop in the field. Now you can see my adjusted bore depths are just under 400 feet the way that I've laid it out right now. Something that's probably worth pointing out in the state of New York, you've got some regulations that start to kick in as soon as your bore depths are greater than 499 feet. Is that correct, John?
That's right. You got to buy another permit.
Got to buy another permit, so it'd probably just be best to stay out of the regulator's inbox and keep your bore lengths to shallower than 499. Right? Makes life easier. So based on that, right now the way this system is designed, 3 bores, spaced 15 feet on center, with a 0.4 grout connectivity, you'd have to put in 3 bores, 391 feet to maintain a 30-degree minimum EWT value in heating mode. Okay. So if you're very specific about when you go to your drilling contractor, ask them for a ground loop. Don't go to them and tell them I want a 7-ton loop field. Go tell them I want 3 bores to 400 feet deep with this spacing and this grout. Be very specific about what you're asking for, right? But a couple things to point out here is notice the difference between the bore depth and the adjusted bore depth on the screen. So if you remember from the zone summary page that I showed earlier, the ground load imbalance was what, 90 million BTUs taken out of the ground versus about 20 million BTUs per hour, or BTUs, excuse me, put back in the ground in cooling mode. We've got a relatively imbalanced annual ground load. And now you'll notice, that's why you're noticing the difference between the bore depth and the adjusted bore depth here. The bore depth is the amount of pipe, theoretically, that you'd have to put in the ground to satisfy your heating constraints and satisfy your heating loads given the layout that you've provided here the first year of operation. The adjusted bore depth accounts for that ground load imbalance, so this is theoretically how much you'd have to put in the ground to satisfy all your constraints and account for the imbalanced ground loads over the long term, over the life of the system. So one thing that you can do, and I just want to point this out, that has a minor impact, It has a much bigger impact in poorer soils, especially in the south where cooling dominant and you dump a lot more heat than you extract. But one thing that you can do to offset or counteract ground load imbalance is simply space your bores out. So by going from a 15 to a 20-foot spacing, you can see my bore length dropped from the 390 feet to 365 feet per bore, times 3 bores. And basically what you're doing there is you're giving each bore access to more soil, more volume for storage, for thermal energy storage, and it mitigates that ground load imbalance effect that we were seeing because this is such a heating dominant system. Another thing you might be able to play around with is a thermal grout connectivity. Notice that we've got a drop down here. It shows all of the options, but a 0.4 grout is generally a standard non-thermally enhanced grouting product. It's as simple as it gets. It's simply bentonite with a certain amount of water pumped into the hole in slurry form, and it sets up like peanut butter. But as you can see, standard bentonite grout doesn't have the greatest connectivity. For any value above a 0.4, that's considered to be a thermally enhanced grouting product. So to get your bentonite grout to have a connectivity that's higher than 0.4, you have to add something to the mix. So you either add silica sand or you add graphite. Those are really the two options that you'll see in the industry. With thermally enhanced grout, though, you're basically just following a manufacturer's mix instructions. So you have to add a certain quantity of water, a certain number of bags of each component, and then if you follow that exactly, you'll be able to deliver whatever connectivity is specified. So you can see the impact of going from a 0.4 grout connectivity, let's say, to a 0.88 grout connectivity. It drops our bore lengths from 365 feet to 280 feet per bore. It took a huge bite out of our ground loop design. So you can see the considerable impact that grout connectivity has on your design, and keep in mind that grout connectivity is something that you as a designer can specify. You have control over, and it's something that when a driller follows a recipe, they'll actually be able to deliver specifically. So going from a 0.4 to a 0.88 grout, you can see dropped quite a bit off of our ground loop design. And to give you an idea, as I said, this is just bentonite and water. A 0.88 is bentonite and water and 200 pounds of silica sand in the mixture. Going from a 0.88 to a 1.2, one thing that you'll notice is the law of diminishing return starts taking effect. Going from that 88 to the 1.2, you go from a 200-pound sand mix to a 400-pound sand mix, doubling the amount of sand that you put in the hole if that's the thermal additive that you're using. And you can see my ground loop design links actually didn't change nearly as much as they did by going from no sand to the 200-pound sand mix. It's similar to, if you think about in terms of law of diminishing return, you think about a house with no insulation versus a house with R19, you'd see considerable savings there. And then if you go from an R19 to an R38, you'll see considerable drop-off relative to the first efficiency gain that you had by insulating from 0 to 19 in the first place. But this would be a decent design here, 3 bores to 260 feet. Notice that I expressed a little bit of concern over the flow rate relative to the depth for the first pass at our design with 2 bores. But considering how shallow these bores are, I'm going to go ahead and go back now and let's go to our 2-bore option, spaced 20 feet on center with a 1.2 grout. Now notice those bores are less than 400 feet each for this entire 7-ton system. Even though the flow, GPM per flow path is a little bit higher, I'll take a look at my pumping power calcs, but this is probably the design that I would run with personally. 2 bores to 400 feet with that 1.2 grout would serve this entire system. So let's go ahead and save that. And now you can see we've got a vertical bore design that's been saved and applied to the project. Next, take a look at maybe a slinky design. Does that sound like a plan, John?
Yeah.
Okay. So I've actually got a pretty cool tool to show you to look up soil properties for horizontal as well. And this is a link that we've actually got built into the software, so it's a whole lot easier for me to get to. I apologize I couldn't show you that web page on the previous, the vertical bore design. But when you come to horizontal trench design, first thing you have to do is specify your earth temperature data location. The reason that we ask for it on this page, even after we've asked for a bin data location on the project details page, is because the locations in this table aren't one-to-one. Notice the choices in New York, there aren't near as many of them as there were with the bin data location. So you just need to find the location that's nearest your project, not necessarily geographically, but nearest your project in terms of mean earth temperature versus average air temperature. So try to pick a location that matches wherever you're working the closest in terms of that value there. Once you've specified that, the next thing you need to do is specify your soil properties, right? And soil properties always seem to be the biggest black box for most people. They bring up the most amount of uncertainty in the design. So one thing I want to show you here is I clicked on the calculator, and notice that we've got a little link here that's going to point me to an external site. I'm going to go ahead and grab that. It's going to bring me to the USDA Web Soil Survey, which, if you haven't seen this, is actually a pretty cool little tool. Okay, John, I'm going to ask you here.
7523.
7523.
County House Road, Auburn, New York.
Okay. So again, this is Web Soil Survey. If you haven't, I suggest you check it out. You can just Google search for that. It'll take you right to it. But as soon as I pop in this address, I'm going to go ahead and hit View.
Hey, there I am.
There's your building, right? Looks familiar?
Yeah.
Have you seen this before, John?
No, I haven't.
Okay, so let's go ahead. Here's your building. I'm going to click one more time to zoom in. And basically what you can do here is for any address in the U.S., you can look up by address, and then I'm going to go ahead and click on the define an area of interest just by drawing a rectangle. Let's say I'm going to put in a horizontal loop field right here on this side of the building. So I'm going to drag an area of interest there. Okay? So now as soon as I've done that, it's looked up all the soil maps, soil data that we have in the area. So I'm going to click on the Soil Map tab here, and you can see in that little square that I drew right beside John's office, it's showing me two different soil types. One is about 64% in that area, and the other is about 37% in that area. And if you want to see what the soil type is, you can just go ahead and click on this link here. It'll pull up a little window and give you all the information that you need. A lot more than you need actually, but here you can see what we're interested in is the burial depth of the pipe. So you see right there from 36 to 60 inches, it's silty clay loam. And if you want to see what the other one is, the other soil type, go ahead and click on that. And again, they'll give you a whole lot more description than you probably need, but again, from 30 to 40 inches deep, silty clay loam, very similar. So after having looked that up, I'll keep that in mind when we go ahead and choose our soil. But just to show you, if you want to actually generate a PDF report of this, go to the shopping cart. I don't know why they call it shopping cart because this is a free service, but I'll show you. You go to the shopping cart. You can type in a title for the report, and then all the different options that you want to include in the report, you can go ahead and check or uncheck those. Click on Checkout, and then once you do that, you can hit Get Now and hit OK, and it'll actually pop open. It'll generate the PDF and it'll pop open a new tab. It might block me here if you've got a pop-up blocker enabled, but you could also click, see right there, it says we got a pop-up blocker enabled, but you can go ahead and hit Checkout and actually hit the download button, and it'll put a PDF right on in your download folder, wherever that is on your computer. And it gives you a pretty thorough and detailed report when you do this. So if you want to look like you've really done your homework in identifying soil type on a job site, there you go. Now you can pop in, you can hit OK, it'll email to you whatever you want to do. And it'll be like a 30-page long report. But all you really need is the little bit of detail that we got before, which is silty clay loam, right? So now coming back to this page here, let's go ahead and take a look at all of our soil type, soil descriptions here. It's not necessarily important to pay attention to the actual names, Benclair versus Sharpsburg, etc. These are all the soil types that are listed in the IGSPA manual. But what is important is to try to grab the soil that's got the description that matches what we just looked at. So in our case, silty clay loam, which you can see is very small percentage of sand, but 60% silt, about 40% clay. That closely matches the description of what we looked up. So I'm going to just go ahead and grab that and hit apply. So that little lookup there took out some of the guesswork of trying to pick out the right soil from that table. And notice I skipped over, but I didn't mess around with any of the density values or moisture values, but you can if you prefer. I generally recommend just leaving those at average and at typical, basically the middle settings, unless you've got better information, unless you know there's a very high water table, or you might be in an area that'll experience periods of drought, whatever it happens to be. So with your soil properties identified, the next thing that you need to do is specify, again, ground heat exchanger material, loop size. For the most part, you generally want to stick with a 1 loop per ton layout with horizontal trenched. And what that means is you want to stick with 3/4 inch loops and a 1 loop per ton layout. Because those larger pipe sizes can become difficult to wrestle with, especially if you're trying to bend them into a slinky shape or whatever it happens to be. So I'm going to stay with the 3/4 inch loop. But now, the last thing you have to do is specify your configuration. And as you know, there are many, many, many different ways to bury pipe in the ground to get the heat transfer that we need. This is a 7-ton system, so I'm just going to show you what a 7-pipe racetrack looks like. So if you want to go out in the yard and dig a huge pit and lay racetrack pipe, just like we're showing in the picture here, you can do that. You can design it to provide all the heat transfer that you need for the system. Or you can go ahead and come in and choose a standard configuration, maybe a 4-pipe rectangular, something like this. And this is a relatively easy configuration to install. You drill or you dig a trench of a width that you can specify, and you can actually just put a U-bend in the bottom of the trench, put a couple feet of dirt in, and put another U-bend 2 feet above, right? So you can do that sort of thing. Probably when you're talking about standard configurations, the one that you see, or horizontal configurations, excuse me, the one you see in most magazines and pictures, it's probably the slinky, right? We've all seen a picture of what a slinky looks like. These are all the options that we have inside the program. So there's an 18-inch pitch slinky, one that you'll commonly see used. Notice that the diameter of each coil is 36 inches. So when this pipe is extruded in the manufacturing facility, it's pulled off the extrusion machine when it's somewhat warm, and they coil it. And those coils are about 3 feet in diameter, about 36 inches in diameter, and the pipe cools that way. So you notice it's got a little bit of natural memory to it. So you generally don't want to fight the memory of the pipe. Just stay with the 3-foot diameter coils. And then by 18-inch slinky, what we mean in terms of the pitch is the spacing from one point of a slinky coil to the same point of the next. So with a 36-inch diameter in an 18-inch pitch, half of each slinky loop overlaps, each slinky loop overlaps half of the previous. So that's what that means. And notice we've got an 18-inch slinky and an 18-inch standing slinky. There's no difference in these in the way they're constructed, except a standing slinky is standing on its side just like this in a trench that maybe you've dug with a chain trencher instead of a backhoe. So we allow you to specify those differently as well. So let's go back to our laying 18-inch option. We got a 3-foot wide trench. Let's go ahead and maybe say 4-foot trench depth and a 3-foot center to center spacing for the time being, so 4 feet below grade. A 3-foot center to center spacing with these being 3 feet wide, basically 3 feet from the center of this one to the center of the next. We're touching each other on edge as far as the way this is configured. So instead of individual trenches, a system like this would most likely be installed in a pit. This is a 7-ton system, so let's go with 7 trenches total. So now, if you come down here, You can see we're at a 1 loop per ton design, roughly, so you can see 3 GPM per flow path. You'll see the amount of pipe that we have to install in this specific configuration to satisfy our heating requirements. 24,000 feet of pipe, 3,400 feet of pipe per slinky loop, 424-foot trenches. Obviously, this is a silly design, but what I want to show you is how a couple of these inputs have a large amount of impact on your calculated lengths. So the first thing we can do, instead of digging a 4-foot trench depth, I want to show you how sensitive the calcs are to the depth overall. So the first thing you'll notice is that with a 4-foot depth, our predicted soil temp at that depth in the end of January is 38.5 degrees. We're trying to design for a minimum EWT value of 30. There's not a whole lot of delta T that we're allowing our system there, which is part of the reason why our trench lengths and our pipe lengths are so long here. So let's see what happens if we go from a 4-foot depth to an 8-foot depth, just to show you the impact there. Now look what happens to our predicted soil temp. It's 47 degrees instead of 38. So we basically doubled the amount of delta T that we allow between our loop and the soil. And you can see what happened to the total pipe length, 13,500 feet down from the 25,000. Same thing for the pipe length per trench and individual trench length here. Had a huge impact. The other thing that you can do is see the impact of spreading them out. So rather than touching each other on edge, let's spread them 10 feet on center. So by doing that, you can see we drop our total pipe length down from whatever it was down to 8,500 feet of pipe, 1,200 feet per trench, about 150-foot trench lengths. So there are some factors that you need to consider, though, when you're laying out a horizontal loop, though. Obviously, when you go to an 8-foot trench depth, you're going to have to deal with some OSHA requirements that might get to be expensive, right? If a trench is deeper than a person's height, then you have to do a shoring or something like that, right? Which might become expensive. I'm ignoring those things right here in the layout just to show you the impact of all the inputs here. One thing that you generally want to try to do is to get your individual loop lengths here to 800 feet or less. I generally try to shoot for a 500 to an 800 foot individual loop length. So one thing that I can show you as well is rather than using the 36-inch pitch slinky, which is generally pretty common, especially in pictures and stuff like that, let's go to a 36-inch pitch slinky. So basically we haven't really changed anything other than spread our slinky out a little bit. So you'll notice in the picture here there's no overlap from one slinky loop to the next. By spreading these out, you lower your pipe density in the trench. So we went from installing about 8 feet of pipe per foot of trench with this 18-inch pitch slinky. It's referred to as an 8-pipe configuration. Dropping it down to a 36-inch pitch, that's considered a 5-pipe configuration. So this is 5 feet, or this equates to 5 feet of pipe per foot of trench. So by spreading them out this way here, you can see what happens. As you would expect our trench lengths to go up a little bit, and they did. They went up from 155 to about 160 feet per trench. But take a look at what happened to our individual coil lengths. They dropped from 1,200 down to 800 feet. And again, you want to shoot for 800 feet or less on your individual coil lengths here. Considering all the changes that we made, this could be one solution that you propose to the homeowner in terms of horizontal design. One that I've moved to a lot lately around here is I actually like the standard configuration and a 2-pipe length like this. And my reason for that is because we've got an installer here in the area that's got, it's an old, some sort of, I don't even know what it is, a trenching machine that he uses to put in big pipe at dairies. But basically, what it is it'll dig, it's a big wheel that'll dig a 7-foot deep trench, and we're able to do about a 300-foot long trench in 20 minutes. So basically what we do is we dig a 7-foot deep trench that's 2 feet wide in a matter of about 20 minutes, and then we drop a U-bend in the bottom and then push the dirt in. So we're ending up with about 250-foot long trenches, and we just buy a 510-foot 3/4-inch U-bend and put it in the bottom there, and you've got extra feet on the end of the pigtails. But obviously, when you do something like this, it takes a much bigger piece of land to do that. But notice how much less pipe length I have with that configuration. Individual pipe length per trench. We might get away with a more reasonable pumping solution with these shorter loop lengths than the slinky I showed before. So, but once you're done playing around with this, now you can go ahead and save it to the project. And now notice that we've got a vertical bore design and a horizontal trench design loaded up in the project. You can show the homeowner option A and option B. As far as heat transfer and system performance, the only thing your heat pump cares about is how much flow you give it and what the water temperatures are under worst case conditions. So theoretically, both of these loops, the vertical bore and the horizontal trench layout, both have been designed to deliver the same performance as far as the heat pump is concerned, ignoring pumping differences, right? So basically you can go to the homeowner, give them both options, assuming they have room, give them the costs, give them the basically pros and cons for each. Probably the biggest con of the horizontal trench would be the amount of dirt that you have to move, the amount of disturbance on the site, but most likely you're probably going to be able to put it in for less than you would with a vertical bore that requires specialty equipment in the drill rig. So with that, I think we're running up on time here. I'll skip the econ stuff. I think you guys have already seen that in an earlier presentation, but I'll show you here. Once you get your project buttoned up and you're ready to share a report with the homeowner, you can go to the project summary page here. I'm going to uncheck all of the boxes here that are related to econ, but other than that, every single section that we filled out inside the program is an option that you can choose. And then once you're ready, go ahead and hit generate, and you'll notice a new tab will open up in your browser window. Depending on your internet connection, it'll think for a few minutes, and it'll generate that PDF report that you can save to your computer, print off, email and share it with your homeowner, whatever it needs to be. So, and I guess with that, do you guys have any questions for me?
Come on, don't be bashful, guys.
I don't know, this is a lot to take in.
Yeah.
I'll tell you one thing. Over the years, I've tried all the different software that has evolved, from Elite to Glee Pro to so many different flavors that have moved through the industry over the past couple of decades. But truly, this looks remarkable to me, especially that the subtle tools they've built into this with just the access to soil information is a powerful tool. Building a vertical analysis to estimate conductivity. So indeed, my hat's off to Ryan and his team for developing this, and I know we've used the LoopLink Pro on the commercial jobs and found that to be tremendously helpful. But I really hadn't kicked the tires on this residential package, so I'm very impressed, Ryan. Well done.
Yeah, thank you, sir. And thanks for having me on. Sorry, everyone, for the trouble in getting logged on to that, but we made do. John came up with a clever solution. So, but yeah, I'll be at the New York Geo Show walking around this week. So if you guys are going to be there, I'd really like to chat with you. So make sure you stop by, say hi, whatever it is. And John, I think I probably owe you a beer or two. So we'll be sure to catch up and get that done too.
And I'll certainly remind you. No, I appreciate you doing this, Ryan. And guys, if there's no other questions, I'll bid you all a good evening, and thanks for being a part of this first attempt to do AI training, leveraging video content with a little bit of extra interaction via these webinars. and I will be sending out a bit of a evaluation sheet for you to really share with me your perception of the experience and what you've learned. So be looking for that. Any final words from anybody?
Yeah, I got a quick question. Now we absolutely have to get that quiz done, right? Or
well, I gave you a choice. You could either take the online quiz, which will be, if you get 80%, you will achieve the IGSFA accredited installer credential. And that's all NYSERDA is looking for to participate in the rebate program. So you can take the test online, or you could do both. The other option is to come to the conference, and right now I believe there's 11 of you that have signed up to come to the conference to take the NATE proctored exam, which would give you the additional credential of being NATE certified.
so should I do both? I mean, I'm coming to the conference. Should I take that quiz?
I would, just for the heck of it. And if you pass, then you've achieved the IGSFA requirement. And if you come to the conference and you pass the NATE proctored test, then you would get the additional NATE certification recognition.
Okay.
So it's sort of up to you. You could take them both or not. It's up to you. But to remind everybody, once you click on that button to take the quiz online, you've got 2.5 hours to take it. Generally, my experience is 60 to 90 minutes, just about everybody finishes. Ryan, you've probably conducted a lot more of these than I have, but what have you generally seen?
Yeah, I think generally, it boils down to the preparation for the exam. It's not difficult, but, it's open book. So you kind of will have familiarity with where the materials are in the book and those sorts of things. I can't stress enough to you guys, work your way through that study guide. If you're comfortable with that, you will do very well in the test. I think, John, did you guys cover any fusion-related stuff?
We really haven't. There is some videos as part of the online content that do expose the students to some fusion, but we are bringing our tools to the NIGEO, and any of you who want to do hands-on fusion training, stop by our booth, and Mitchell, our lead technician here, will gladly walk you through it.
Yeah, I would highly recommend doing that. At least on the paper version of the exam, there are a number of fusion questions. So definitely a great idea to stop by and get up to speed on those, on fusion procedures. So
very good.
Yeah, fusion question on the exam.
Pardon me?
There's fusion questions on the exam?
Yes.
Yeah, there are.
But they're not in the study guide, though, are they?
Right. So, John, do you still have a copy of the old fusion study guide that we handed out back when we were doing the heat spring training
I don't.
years ago?
I may have, but it's so buried in files that I probably couldn't find it.
Yep. So we have it online. We have it. I'll see if I can get you a copy so that you can share with the group before they take that exam.
I would very much appreciate that.
Yep. You guys will want that.
Okay.
Okay. Any other questions?
Thanks, John.
Thank you, Peter, and everybody else. And
Thanks,
we'll call it an evening. So we'll see some of you guys later this week. Otherwise, I hope to reconnect with you guys in ways in which we can further help you ride the curve, the learning curve that never stops.
Mm-hmm.
So,
Thanks, John.
thanks,
Thank you,
guys.
everyone.
Yep.
Thank you.
Bye-bye.
Look forward to seeing you this week.
Thanks, Ryan.
Take care.